Hello, this is Mrs. Scarpo, and this is part 2 of Unit 1, Lesson 5, the tortoise and the hare lesson. We left off in the last video comparing the tortoise with the hare and the functions that they had, the tortoise being an exponential function and the hare being a quadratic function. In this situation, would the hare turn out better if his function was 2x squared rather than just x squared? So I have gone ahead and created a graph using the same colors that I did in video 1. So the red parabola is that of the hare, and the green curve is the exponential curve, and you're able to see also the side when x is negative what those full curves look like. So the green is the tortoise, the red is the hare, and we can see down here at the bottom that for a little while the hare was ahead of, or the tortoise, excuse me, was ahead of the hare because its curve is above that of the tortoise, or of the hare. And then for a while, it looks like the hare is ahead of the tortoise because the red curve is higher, has higher y values than the green curve. But then we get up here and they switch again. So if the race were less than 7 seconds, it might be more beneficial to the hare. But after let's say 6.3 seconds, it appears that the tortoise starts gaining on the hare again. So is multiplying the x squared by something going to make it increase faster than just an exponential? It doesn't appear that way. It appears that the exponential still grows faster in the long run. So what are some takeaways that we have from this particular lesson? The shape of the graph of a quadratic is U-shaped. It's a parabola. And it does have symmetry, so one side of the parabola should have the same shape as the other side. So this is a sample of a parabola, what you would see with a quadratic function. With an exponential function, as we saw with the tortoise on that last screen, and it probably also looked like this side where the x is getting smaller, that the curve ended up on top of the x-axis. It'll get really, really close to the x-axis, but it'll actually never cross the x-axis. And when students ask me why that was the case, I said, well, if we keep dividing to get the next value, we're never going to get exactly 0 because you can't divide and get exactly 0. We can get really, really close, and I could zoom in on the graph and I could see that there's a little bit of space between this end of my curve and the x-axis. But then we notice when it's increasing, it comes up rather quickly when it's exponential. So this is the shape of an exponential function. When it comes to equations, you're going to have an x squared when it's quadratic. You'll notice that x is in the base. When it comes to exponential, you'll have some number to the x. In this case, we say x is the exponent. When it comes to a table, we've seen more than once that the constant second difference, or that the second difference is constant, with an exponential function, we have a constant ratio. We have a constant multiplier. So like with the tortoise, we kept multiplying by 2. The rate of change for a quadratic function is described as being linear. That first difference, we could write the equation of a line for that first difference. The rate of change for an exponential function is exponential. It's the one function that its rate of change matches the name of the function. So then we have this exit ticket. Given f of x equals 3 to the x and g of x equals 3x squared, which function has the greatest average rate of change in the interval 1, 3? So what we did in class was we created a table where we had the x values 1 and 3. We had the functions 3 to the x and 3 squared, or 3x squared, excuse me. And we found the values for each function at 1 and at 3 so that we could determine which one had the greatest average rate of change. So when x is 1, we have 3 to the first power, which is 3. And when x is 3, we have 3 to the third power, which is 27. Going to the quadratic function, we would have 3 times 1 squared. 1 squared is 1. So 3 times 1 is 3. We have 3 times 3 squared. 3 squared is 9. 3 times 9 is 27. If we look at the interval from when x is 1 to when it's 3, we actually see the same values. So neither function has a greater rate of average rate of change, because the average rate of change is the same. In the long run, which function will have the greatest y values for very large x values? Anytime you see a question like this and you're comparing an exponential to a quadratic, your answer will be the exponential. Exponential functions always have a greater rate of change in the long run for large values of x than the quadratics. Now is some time for some review from Algebra 1. Determine whether each representation is a function or not a function. If it is not a function, describe what you would do to change it to make it a function. So as a reminder, function is defined as every or each x value is paired with exactly one y value. So if I look at this set of points, all of these are x, y points. They're all ordered pairs. We have 2, 7, 3, 9, 4, 8, 5, 5, 6, negative 3, 7, 5, 3, 7. As I go through and I'm pairing or comparing x values with y values, I see there's only one x value of 2. There are 2 x values with 3. So if I look at those 2 points, they have the same x value, but they have different y values. This is not a function. Because there are 2 y values paired with the 3. It could be fixed by, I see there's a pattern on the x's here, and this is not by any means the only way to fix this, but it could be fixed by changing 3, 7 to 8, 7. We would then have different values of x in every single point. So what you want to do is make sure that you don't have any x values repeated. With the graph, you may remember something called a vertical line test. If I move this line from side to side and I see where it crosses the graph, will it ever cross or touch more than one point on the graph at a time? Hopefully you're seeing that as I move this line across the screen, that the green line only ever touches the graph at one point. So we would describe this as a function. And we could say because it passes the vertical line test. The next problems in our review are stating the domain and range of each graph and using interval notation where appropriate. So for graph number 3, we're going to write the domain, which is the x values used, and we're going to write the range, which are the y values used. So if I look at this graph and I go from left to right looking at x values, it appears that every x value on this graph is being used. Because I don't see any dots, I don't see any points on either end of my graph, like I see in the middle of my graph when it changes direction, I am going to assume that this graph can continue on. So based on what I see on this graph, my domain is going to be negative infinity to infinity. My range, however, doesn't seem to go any higher than 7. That seems to be my highest. And because these ends are each coming down, and we're assuming that the domain continues, we're going to say that our range will go from negative infinity, so any value down below, up to 7. And I'm using a square bracket on the 7 because we're including that value on the graph. If we look at the graph for number 4, we're going to do the same thing. Find the domain, which is x values, and the range. What is different about this graph is we know that it has a definite ending and starting point. So this graph goes as far left as -3 and as far right as 10, with solid points at each end, so we can define the domain as being from -3 to 10. the range, its highest point is at 4, its lowest point is at -1. And when you write these interval notations, you always start with the smaller number first. So it goes from -1 to 4 is our range. And this concludes the end of Lesson 5 from Unit 1.